Here we're going to consider colligative properties. Colligative properties are properties of the solvent in solutions. There are four colligative properties: vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. Now, in terms of vapor pressure lowering, we already considered that thermodynamically, and we ended up for an ideal solution, Raoult's law, meaning the pressure of some component above the solution is equal to the mole fraction of that component in the solution times the vapor pressure of that pure component. So the mole fraction always has to be less than 1 or less than 1. So therefore the vapor pressure of a solution will always be less than a vapor pressure of the pure component. And that's Raoult's law, vapor pressure lowering. All right, let's look at freezing point depression. Now remember from introductory chemistry, this equation was just sort of thrown at you. The freezing point depression was equal to this molal freezing point depression constant, Kf, times the molal solution concentration. What we're going to do here is to get this equation by some more fundamental thermodynamic considerations. So what I want to do is to make the argument that here we have, I'll put open circles to be the solvent. There's our solvent. And then within the solvent, we have these filled in circles, and those would be the solute. And we're going to say that we have much more solvent than there is solute. So the solute would be the component that's in lower concentration. So let's consider this sort of pseudo reaction. Let's call the solute A and the solvent B. So let's take the solid of the solute, and let's take some solvent. That's a solvent. And we're going to take some of this and solvate it. So now we have a B, which is solvated. So for example, if you dissolve something in water, say sucrose or something, sucrose then would be dissolved. It would break apart from the solid and be individual molecules, so these would be sucrose molecules. And like we did for when we considered the temperature dependence of solubility, here we're going to consider boiling point elevation. We're going to consider this as just a liquid. The solute now is a liquid dissolved in the solvent liquid. So it's like a liquid-liquid solution. So I think what we can immediately say, if you like that argument, just go back in the previous part of this lecture, lecture 12b, and look at that derivation. And what we found there was that the natural log of the solvent concentration expressed in mole fraction, actually what we're looking at the solute, but here we're looking at the solvent because we want to look at the freezing point depression of the solvent. So initially the solvent is pure, but now because of this extra, quote, liquid we got by dissolving the solute, solid in there, the mole fraction of the solvent has gone down. Well, analogous to what we did before, the natural log of the mole fraction of the solvent will be the enthalpy of fusion divided by R, 1 over the temperature minus 1 over the freezing point temperature. All right, so we're making an analogous argument to the argument we made when we considered the temperature dependence of solubility. So that's where we're going to start. You might review that and look at the similarities. We really want, I don't know if we really want to do it, but what people usually do is to express the concentration not of the solvent but the solute. For a two-component mixture, the solvent is 1 minus the mole fraction of the solute. So that would be equal to minus delta H of fusion over R. 1 over T minus 1 over freezing point. This would be the freezing point of the pure solvent. Okay, well, maybe you've heard about Taylor series, and maybe you heard the expression for mathematicians, Taylor series is your friend. So what we want to do is to expand this expression in a Taylor series about the point x equals 0. So just to refresh our collective memory, a function x be expressed as the sum for I equal 0 to infinity of 1 over I factorial, the ith derivative of f with respect to x, evaluated at the point x equal x0 times x minus x0 raised to the ith power. So this expands a function about some point x equal x0. So let's expand the function f of x equal natural log of 1 minus x solute. I'll just omit the solute here, but remember that's solute, about x equals 0. All right, so let's take the first term, this Taylor series expansion. That means I is equal to 0. So for I equals 0, we have 1 over 0 factorial, the 0th derivative of f with respect to x, evaluated x equal x0. That should be a 0 down here, I guess. And then x minus x0 raised to the 0th power. We know from factorials this is equal to 1. This, the 0th derivative of the function, is just the function. The function is ln of x, so ln of 1 minus, and we're going to evaluate this at x equal x0, and we said x0 was 0. So we'll just evaluate this x equals 0. So 1 minus x, 1 minus 0. That's what that term is. And this term will be x minus 0 raised to the 0 power. All right, this is equal to natural log of 1, which is 0, and this is equal to anything raised to the 0 is 1. So this, the I equals 0 term, is equal to 0. Now let's do the I equal 1 term. Again, what we're doing is we're just taking the first two terms in this expansion. So I equal 1, we'll have 1 over 1 factorial, the first derivative of the function with respect to x, evaluated at x equals 0, and we have x minus 0 raised to the first power. This is equal to 1. The derivative of f of x, recall that f of x is ln of 1 minus x. So when you take the first derivative of here, we get minus 1 over 1 minus x, and we're going to evaluate this at x equals 0, so that's a 0. And here, that is just x. So we multiply all this out. The I equal 1 term gives, this is a minus 1 minus x. So what this means is the natural log of 1 minus the solute mole fraction is just equal to minus the solute mole fraction. All right, so that's a handy thing to be able to work with, those Taylor series expansion. So we go ahead and substitute that in our equation a while back. So we get minus x to the solute. That's equal to minus delta H fusion over R 1 over T minus 1 over T freezing point of the pure substance. This will be the freezing point of the mixture. All right, so what are we going to do now? Let's cross multiply. So if we cross multiply, this term will be freezing point minus of the pure stuff minus the freezing point measured over T minus T times TF. All right, and let's get rid of that minus sign on both sides. We get that the mole fraction of the solute is equal to delta H of fusion divided by R times the freezing point of the pure solvent squared times the freezing point of the pure solvent minus the freezing point of the solution. And this we're going to call delta T, the freezing point depression, the lowering of the freezing point. So there it is, but it's not quite yet in the form that was presented in introductory chemistry. The mole fraction, or the mole fraction of the solute into molality. We did that once before. Let's do it again. So the mole fraction of the solute is equal to the moles of the solute divided by the moles of the solute plus the moles of the solvent. And we're going to say that's about equal to the moles of solute divided by the moles of the solvent when we have a dilute solution. Dilute solution means the moles of the solute is much less than the moles of the solvent, so this sum is about equal to the moles of the solvent. Now, recalling what molality is, so molality is moles of solute per kilogram of solvent. All right, we compare these two units. Looks like the numerator, moles of solute, is okay, but we got to convert moles of solvent to kilogram of solvent, and we do that by multiplying by the molar mass. So this is moles of solute over moles solvent, and we multiply here capital M, molar mass of the solvent. So molar mass of the solvent, it's expressed, say, in kilogram per mole times moles of solvent. This term then will be kilogram of solvent. And then therefore this term, these terms here, will be equal to the molality. So our conversion factor, X of the solute, the mole fraction of the solute, is equal to the molality of the solute, I don't need to put that there, that's what's implied, times the molar mass of the solvent. All right, so now that we know that, we can convert this concentration in terms of mole fraction to molality, so that M times M, that's the mole fraction, lowercase m molality, uppercase M molar mass, that's equal to the enthalpy of fusion over R times the freezing points of the pure solvent squared times delta T, or delta T is equal to the molar mass of the solvent times R times the freezing point of the pure solvent squared divided by divided by, we flip that down there, so this will be delta H of fusion times the molality. And if we define these terms here as Kf, we have the introductory chemistry expression delta T, the freezing point depression, is equal to a constant Kf times the molality. And what have we done to get that? Well, we've assumed that we have a dilute solution, and if it's a dilute solution, then the freezing point didn't change much with when you add the solute, so this can be replaced by a constant. And with those things, we have the intro chem equation like this. And the key point, again, what we did was when we did that derivation, we used Taylor series, that's kind of cool, is that we assumed that the solute was a solid, but then when it dissolves, you can consider that just as a liquid. So the solute going from the solid to a liquid gives you delta H of fusion. Okay, so that takes care of freezing point depression. We know where that comes from thermodynamically. We did vapor pressure lowering, freezing point depression. How about boiling point elevation? Well, you're probably anticipating the solution to that. Let's first give the intro chem equation. The boiling point elevation is the molal boiling point elevation constant times the molal concentration. This again, remember, is the solute concentration. Okay, so where does that come from? Well, again, we'll just use the analogous argument that we used when we talked about the temperature dependence of solubility, and we used that for freezing point depression. We're going to use it once again for boiling point elevation. So here's the solute. I guess we're calling this a solvent, be consistent with our previous picture. There's our solvent molecules, and then we have solute, which is the open circles. Now when we boil something, what happens is that we go from the so-called liquid state, so I'm assuming that the solute here is in the liquid state, the solvent is the liquid state. We're looking at the boiling point of the solvent, so just let's consider the solvent. So what you have to do is you have to take that out of the solution and put it into a gas. So I hope I can convince you that it's just like we had before, that the natural log of the mole fraction of the solute, but now instead of going from the solid to a liquid when we freeze it, we're boiling it, so we're going from a liquid to a vapor. So therefore this comes out to be delta H of fusion, of vaporization. What am I saying? Vaporization over R, 1 over the boiling point of the pure solvent minus 1 over boiling point of the solution. Okay, we'll do the exact same things we did before. We'll do the Taylor series expansion here. We're looking at the solvent, so clearly I'm hallucinating. This is the mole fraction of the solvent, because that's what we're measuring the boiling point elevation of. So we'll do the same thing. A Taylor series expansion gets rid of this. Let's put some minus sign there, but that'll cancel out here. So the mole fraction of the solute, and again cross multiply and so on, is the enthalpy of vaporization over R times the boiling point of the pure solvent squared times delta T, where delta T here is T minus TB, boiling point elevation. Note that the boiling point goes up, so delta T for the boiling point is greater than 0. On the other hand, we'll just go back here and see how we define delta T. So the freezing point goes down, so delta T here is negative, less than 0, because the freezing point is depressed. Okay, so there's different definitions of the delta for freezing point and boiling point elevation. Okay, and then we make the conversion to molal. So we get the molal solution concentration of the solute is equal to R times the boiling point of the pure solvent squared over delta H of vaporization times the molar mass M of the solvent times the molarity, times the delta T. Clearly I got this wrong, so we're going to switch them around here. So delta T, the boiling point elevation, is these things times the molal solution concentration. And we call this Kb. And again, in order to get this relation, we had to assume a dilute solution where the molal solution concentration can be easily calculated from the mole fraction, and also where the boiling point of the solution doesn't differ much from the boiling point of the pure solvent. So there we have it for boiling point elevation. And finally, let's consider osmotic pressure. We considered this briefly when we talked, I believe, Monday or Wednesday, can't remember, about osmotic pressure. Let's consider it once again. So here's the setup for osmotic pressure. You have a chamber, or a cell. It's actually an osmotic cell. People actually do this. Looks something like that. And here we have a semi-permeable membrane. This might be, for example, a biological membrane. This membrane is semi-permeable membrane is permeable to solvent, and it's impermeable to solute. And let's just put some solvent in here. Let's call it H2O, some water. And we fill this up with water till these are capillary tubes here, till the level in the capillary tubes is about equal, or is equal. And of course you would expect these two to be equal because there's nothing pushing water up or down. So when you first start out the experiment, water on both sides, the membrane is permeable to water, these water levels will be equal. Now, say on the right-hand side, let's add something that's impermeable. And typically, if you want to be biological, let's add a protein. But it could be any solute that is impermeable. Now we look at this and we say, where is water more concentrated? Well, by adding the protein on this side, you've diluted out the water. So water is more concentrated on the left-hand side. A more fancy way of saying that is the chemical potential of water on the left-hand side is greater than that on the right-hand side, because chemical potential and concentration are related, logarithmically, but nonetheless monotonically increasing. All right, so what's going to happen when you put the protein there on the right-hand side? Well, water is going to flow down its concentration gradient from a high to a low. So water now is going to flow down the concentration gradient. So as the water flows this side, this water level goes up to here. And as it flows, this water level goes down to here. So now you have a difference in water levels above the solution. On the right, you have a higher pressure than on the left, the hydrostatic pressure difference. And what happens is, qualitatively, is that this pressure, extra pressure due to this water column, cancels out the difference in chemical potential. So the chemical potential makes water go this way, but now this hydrostatic pressure is making the water flow the other way, and when it reaches equilibrium, they balance each other out. The height of this water column exerts a pressure, and this is called the osmotic pressure, which is given the symbol pi. Go back to white here. Okay, now let's call this, say, compartment 1, and this compartment 2. So at equilibrium, the chemical potential of water in compartment 1 is equal to the chemical potential of water in compartment 2 at equilibrium. So let's look at the chemical potential in compartment 1 over here. The chemical potential of water in compartment 1 is the standard state chemical potential of water in compartment 1 plus RT times the natural log of the activity of water in compartment 1. We'll assume that well, we don't need to assume the activity here, so there's no extra hydrostatic pressure difference here. The activity of water on this side will just be 1. It's the pure substance. There's nothing over here. So in fact, the chemical potential water in the left-hand side is just the chemical potential water in compartment 1, standard state. Now let's look at the chemical potential water in the second side. Well, that'll be a standard state chemical potential of water in the second side plus RT times the natural log of the activity of water. Let's assume we have an ideal solution, so I'll just put mole fraction of water on the second side. Okay, and then we have an additional component due to this pressure difference here. So I'll call that mu for osmotic pressure. All right, note that this this component will be negative since the mole fraction over here is less than 1 because we added protein, we diluted it out, and that will have to balance out with this extra chemical potential due to the hydrostatic pressure. Let's look at this extra chemical potential due to hydrostatic pressure. How does chemical potential vary with pressure? Well, we know, or maybe we don't know, maybe we don't remember, but let's do it this way. How mu changes with pressure at constant temperature is just the partial molar volume. So we integrate that. d mu will be the partial molar volume dt. Let's integrate this from what we have on the left. That's from the water in compartment 1 to the water, chemical potential water in compartment 2. That'll be V, d mu, and we're going to integrate the partial molar volume over temperature. Oh, sorry, what did I do? This should be pressure, so apologize there. So d mu dp, dp goes over there. Okay, dp. So this will be from the pressure on the left-hand side to the pressure plus the osmotic pressure on the right-hand side. Okay, so what we have here, this is just regular old water at 1 pressure on the left-hand side. And now we have here water is a lower chemical potential because of the dilution by the protein, but it's a higher chemical potential because it's hydrostatic pressure. We're calculating that extra term for the hydrostatic pressure. All right, so that mu of H2O in compartment 2, the difference in chemical potential minus mu H2O in compartment 1. Let's assume partial molar volume is a constant, so this is just BV, osmotic P pressure on the left-hand side plus that extra osmotic pressure minus the pressure on the left-hand side, partial molar volume. So this equals the osmotic pressure times the partial molar volume. So that's what the extra stuff is for the hydrostatic pressure over here. So this should be a standard state. So what we end up with is that RT times the natural log of the mole fraction of the solvent is equal to minus pi V bar. We'll make our usual assumption of dilute solution, where the mole fraction of the solute or solvent can be replaced by 1 minus mole fraction of solvent in a dilute solution. So this just be equal to minus RT times the mole fraction of the solute, and we did that with the Taylor series expansion, is minus P times partial molar volume. All right, at this stage, we might look at or try to remember what the introductory chemistry equation was for osmotic pressure. It was the osmotic pressure pi is equal to the molar solution concentration times R times T. All right, so this is what we got so far, considering equality of chemical potential at equilibrium and the extra chemical potential due to the hydrostatic pressure difference on the right-hand side. So let's see if we can go from here to here. I think we can. This is a plus and a plus, so that sort of cancels out. And remember, and let's just put it, remember that the mole fraction of the solute is equal to the molal solution concentration times the molar mass of the solvent. So if we just put that in, we have RT times the molal solution concentration times the molar mass of the solvent. That's equal to pi times the partial molar volume. Let's isolate pi. So pi will be equal to RT. Now we have M, the molality, times the molar mass, divided by the molar volume. Now let's look at these terms in particular. Let's put some units on here. So the molality is mole solute per kilogram solvent. The molar mass M is the, we'll put an SI unit, kilogram of solvent over mole solute, kilogram over mole, mole solvent. Okay. And the molar volume is the volume per mole of solvent. Because remember, the solvent is the one that's moving back and forth. So if we start cancel these things out, kilogram of solvent, kilogram of solvent, mole of solvent, mole of solvent, what you're left with is mole of solute per volume. Mole per volume is molarity. So this term is just molarity. Molarity times R times T. Pi is equal to that. So there is the introductory chemistry equation that was just presented, but we got that by considering chemical potential and the extra contribution to chemical potential due to this hydrostatic pressure gradient. All right, so that's it for colligative properties. I think what else we got here? There we go. 1, 2, 3. So those are the 3 other colligative properties that we have. Now, for the last part of this lecture, we'll do some examples.